Okay, all we want to do right now is just understand some ideas. So we're not, okay, there's no homework tonight, so we're not trying to finish this today. We're just trying to use this to understand some ideas. The first idea is review. So in the packet you have, there's a table. You've seen that before. It just shows time and then velocity. And in this story, they're saying that it is the velocity of an airplane. It says the airplane flies in a straight path. So there's our velocity and our time. And as always, the table only shows selected values. The graph is showing all values of the velocity. And so the graph shows the fact that the velocity goes up, goes back down, goes back up. Okay, first thing on the sheet says item A. The symbol S of t represents the position of the airplane at any time. So these are pretty simple questions. We're just reviewing quickly. So it says, what is the meaning of S of 0? You should write on your paper just to remind you if you need to. You don't have to write it if you don't want to. But S of 0 is the position of the plane at time equals 0. Okay, that's all S of 0 means. And so then item B, pretty straightforward as well. S of 40 would be the position of the plane at time equal 40 minutes. So that's just review. Item C says, if we put some numbers to this thing, and we say that the plane's position at time 0 is 10 miles from where it started, I guess that's wrong. So that's just, it's 10 miles from some reference. So look at this drawing that I have on the board. Remember we talked about in Unit 1 that when they talk about an origin, that's not necessarily where the object begins. That's just location 0. And for our class, we're always talking about motion in a straight line. So the plane did not begin at the origin. The plane in this example is beginning at 10 miles from the origin. That's what this means. S of 0 equals 10. Question. Jacob.
I thought that S of t's position. Okay, we're back on track.
2 points. Anybody else? Cool. S of 40 is 97. Sorry, S of 10 is 97. Oh, I'm having trouble. S of 40 is 244. So that's way over here. At 40 minutes into the flight, the plane has a location of 244 miles from the origin. Cool. Okay, I don't recall that we've, maybe I've talked about this a little bit in Unit 1, but we haven't talked much since. Displacement reflects the difference in two positions. Displacement is different than distance traveled, but sometimes it's the same as distance traveled. For example, if the plane at time 0 started here and flew directly to the right and never came back to the left, then at time 40, when the plane is at location 244, the displacement is 234. It's how much the position changed between those two times. If the plane flies in a straight path, the distance traveled will also be 234. However, if the plane does something like this, where it goes to the right and then comes back to the left and then goes to the right again, the distance traveled will be much more than 234. So keep in mind that you'll be asked about distance traveled. You'll also be asked about displacement. They are related but different. Questions? Cool. Item D just gives another example. Says if the plane's position at minute 20 is 152, so that's here. Then it says what's the displacement between time equal 20 and time equal 40. Really simple idea. The plane was at location 152, meaning 152 from the origin. And now at time 40, the plane's at 244. So displacement's pretty simple. We just take and determine how different are the two locations. That's what displacement is, just how different the two locations are. So somebody has a calculator, punch that in real quick. Do it in your head. What is it? 92. Is the packet wrong, the answer in the back?
No, it just says 245.
Oh, interesting. So go with what the packet says. I'll need to fix my document here. This is typed wrong. Thank you, Tessie. So this is 245 in the packet. So this would be 93. Questions? Cool, pretty simple. Okay, just like we can find here, we can calculate the plane's change in position. We can also calculate the change in velocity from one time to another. Don't overthink it. Just raise your hand and tell me what is the answer to item E. Hands up. Come on. These are really easy. Just want to make sure you're with me. What's the answer to item E on the first page? Make sure your phones are all put away. This starts out easy, but like everything in calculus, it will get harder if you don't pay attention. So Mark, what do you got? Fair enough. So the velocity at time 0 is 7. The velocity goes up and down, but if all they're asking for is change in velocity, all we care about is comparing the two velocities. So this would be 0.3. Show me your hands if you knew. 0.2 for Mark. Question? Okay, there's a note on the packet. I've had students struggle with this a little bit. Displacement is change in position. So if they ask you to find change in velocity, don't call that the velocity's displacement. It's not the right wording. It's not how it's said. It's just the change in velocity. So, questions about anything? Awesome. So moving on. So we've done all of that. Page 2. So page 2 says, again reminding you that we have the position at time 0 is 10. And now they say the position at time 10 is 97. So that makes the displacement for that 10-minute period a displacement of 87, just like I believe this picture shows here. So this number here is representing the displacement of the plane for the first 10 minutes of the flight. Questions? Please.
And without calculating it, we couldn't have found S10 based on the information given to us on page 1, correct?
Oh, good comment. Hey, 2 for Cougar. Let's make a little quick summary here. So here's part of what Cougar said, which is good observation. There's no way from the information they gave you to figure out that at time equals 0, the plane is already 10 miles from the origin. Nothing in the packet would allow you to calculate that. It has to be given. Now, after that, we're going to discuss how we can calculate, we're going to discuss how we can calculate the plane's position at time 40, or the plane's position at time 10. So, key idea. Once you know the plane's position at some time, and if you know the plane's velocity, which we have this graph in this table showing us the plane's velocity, then we can calculate other positions. But Cougar's right, we can't just come up with a position to start with. So, there you go. Sweet. Okay, moving on. Okay, so page 2 doesn't have a whole lot there. It just has a big blank space for you to take notes. I'm not sure you need that much space. But basically, we want to talk now, how do we use velocity instead of position to estimate displacement? The first idea is, again, quite simple. We know that the plane has a velocity of 7 miles per minute. I just need someone in the room to say in your own words, what does it mean to say that the plane's velocity is 7 miles per minute? And it's a simple answer, so don't overthink it.
For every 1 minute, the plane goes 7 miles.
It's that simple, 2 for Benji. For every 1 minute, the plane goes 7 miles, okay? So, if I take, let's see, 7 miles per minute, and I multiply by 10 minutes. The units of minute divide out, and because the plane went 7 miles every minute, in 10 minutes, the plane will change its position by 70 miles. That's displacement. In this case, it is also distance traveled, because the plane is only going one direction. But displacement and distance traveled can be different. Questions? Can somebody raise your hand and tell me, give me another example. This is a rate right here. 7 miles per minute. There are all kinds of rates that you encounter in life. On the AP test, there'll be lots of different rates given. Anyone think of any other rate? Like it's always a something per something. Please, Bailey. So we can go distance again and do something like meters per minute. I've seen AP problems where they'll talk about a pile of, say, gravel, and they'll say the pile is so high and it is growing at some rate of meters per minute. Pile of gravel, maybe it's growing at like 2 meters every minute. And then by the same idea, you can say, okay, if that happens for a 5-minute period, 2 points for Haley, that pile will grow by 10 meters in those 5 minutes. Questions? Please.
Does that mean it'll be 12 meters or 10 meters? Is that, do you add the 10 or? Just
Keep talking, Josh. I'm not sure what you mean. Keep going.
So it started at 2 meters, and then after 5 minutes, is it 10 meters or is it 12 meters?
2 points for Josh. This is telling you not how high the pile was when it started. It's just telling you how fast the pile's height is changing.
Oh.
So in this problem here, this blue example, we actually don't know, like there's no information given as to how high the pile is to start with. Does that answer your question? Anybody else? Please.
So we know 7 miles per minute over 10 minutes, that'd be 70 miles, but we also know that at time equals 10, the velocity is 9.5. So how could that be negative? Because it would be moving faster by that.
So Mark, just looking at the table, says, okay, wait a minute, 2 points for Mark. This seems like a rather poor computation, because at time 0, the plane is changing its position 7 miles every minute, but from the graph, and also from the table itself, it's clear that the plane's velocity doesn't remain at 7. So this is not necessarily an accurate computation. It's just an estimate based on one velocity. Please.
Could you find the average velocity between t of 0 and t of 10 to make it more accurate?
So 2 for Jacob. He's saying, hey, why don't we take and say, well, the velocity is 7 at time 0. The velocity is 9.5 at time 10. Let's average those two velocities. And once we have an average velocity, let's multiply that by 10 and get a better estimate as to the displacement of the plane. That is correct. I don't think I've ever seen them ask you to do it that way on the AP test. But it is correct that that would give you a better estimate. Anybody else? Cool. What they actually do on the AP test is this. They ask you to do what is known as a Riemann Sum. Okay, you don't have to remember the name because they're not going to test you on it. But as you're reading AP problems, you'll read that phrase, Riemann Sum. And instead of averaging the 7 and the 9.5, they accomplish the same thing in a slightly different way. They say, let's assume that for the first 5 minutes, the velocity of the plane is 7 miles per minute. But let's only assume that the velocity is 7 miles per minute for 5 minutes. Then we'll assume that for the next 5 minutes, the plane has a velocity of 9.2 miles per minute. So somebody get your calculator out and tell me what the result of that computation will be. You want? And what will be the units, Ammon? 2 points for Ammon. So, similar to Jacob's idea, if I use 2 different velocities, I use the velocity of 7 miles per minute, and then I use the velocity of 9.2 miles per minute, I get a more accurate estimate as to how much the position actually changed in the 10 minutes. Question? Please.
Just for clarification, you're multiplying it by 5 minutes because in those 5 minutes, it's like the velocity is 7 miles for like the first 5 minutes, and for the next 5 minutes, the velocity is 9.2.
Everybody look here. I'm going to give Spencer a ticket for this one. No, it's dead on. You have to be very careful from this day forward to keep track of the fact that when we talk about time, we're going to talk about it in multiple ways. So this time right here, this 5, that is an instant in time, or a moment in time. So that's one way we think about time is, hey, when the time is exactly, minute 5, like a moment in time. What Spencer pointed out correctly is this 5 here is not this 5 at all. The 5 you see here is a duration of time, or a time period. So as Spencer said, the 5 minutes here and the 5 minutes here, they are calculated by taking how far apart these two moments in time are and how far apart these two moments in time are. That's where that 5 came from. That is perfect. Question? be careful. This first example shows a table where from entry to entry, the duration of time is always 5 minutes. That will not always be the case. It's very common on AP problems to have these table entries spaced 5 minutes apart, then 3 minutes apart, the next one's 7 minutes apart. They just vary it, so you have to keep thinking. You can't be on autopilot. So, question? Awesome, well done. Okay, next thing. Okay, when we said that the velocity of the plane was 7 miles per minute for the entire 10-minute duration, we were able to calculate one possible estimate of the plane's displacement. Nice with the glasses. When we change and we say, let's use 2 different velocities within that 10-minute time period, we get a better estimate. We get a better estimate. So don't overthink it. Just raise your hand so I know you're with me. How do we get an even better estimate? Like there's an idea here that you're going to use over and over and over again for the rest of the year. How would I get an even better estimate of how much the plane's position changed during those 10 minutes? Just extend the idea. Hands up. Come on, who knows? How do I get a better estimate? So we've got a few people who feel like they're with me. The rest are a little uncertain. Let's go with Derek.
You just shorten the time periods you're measuring to add them together.
Yeah, here, and what I think of it is like, I call it sampling. That comes from some of my work previously. We've got this velocity that's changing, and all we're doing is saying, well, how often are we going to check the velocity? So here we check the velocity at time 0. We don't recheck it until time 5. And so if we're only using 2 velocities, when we compute the displacement, we get an estimate. If we want a better estimate, we should sample more often. We should check the velocity more frequently. Here's an example of that. So hands up if you knew that's what he was going to say. Point 2 for Derek. Question? Please.
It's like, you just take, I guess it would be like B prime, and you just have that as, like you take how fast the velocity is changing, use that, multiply.
Oh, I know what you're saying. Let me say it back to you.
Yeah.
Let me say it back to you and see if we're on the same page. So Benji's idea is, well, now we won't do that in this class per se, but the idea is logical. You're saying, if I can find out how fast the velocity is changing, I can compute what the next velocity will be.
Yeah.
And then I can use that to calculate displacement. That's accurate. I don't think they've ever required you to take that approach for this class, but that makes sense. Good point. Is that your question? Yeah. Okay. Anybody else?
I thought we were going to do that.
Okay. Look at this example here. Let me get this a little bit bigger. Okay, look. Okay, this graph in orange. The graph in orange should look pretty much like the graph you have on your paper, same rough shape. Okay, the graph in blue is a mathematical model of the orange. So it means I came up with a formula that tracks the orange pretty well. Okay? Here's what I did. Let's make this a little bit bigger. Come on. It's a little hard to control. Okay, here's the numbers you need to pay attention to. Look, okay, this is the table that's on your paper. It says at time 0, so time 0, let's try and get this to work on the video. So here's time 0. So at time 0, your paper says the velocity is 7, correct? And then it says at time 5, the velocity is 9.2. And then at time 10, the velocity is 9.5, etc. So I created a mathematical formula that will track that reasonably well, not perfectly. So here's the results of my formula. Time 0 velocity is 7.2, 5 I got 9.4. So there's a little variance, but not a lot. That kind of an idea. Okay? And that allows me to sample more frequently. So right here, we're doing what we talked about. We're saying, okay, if at time equals 0, we're going to use the model. The velocity is 7.2. We multiply that by 10, we would find that the plane had a displacement of 72 miles in that 10 minutes. That's what the spreadsheet's showing you. Questions? Okay? Now, if we sample more frequently, so here I'm sampling every 5 minutes. So in the first 5 minutes, the velocity was 7.2. Then at minute 5, the velocity changed to 9.4. That means in those first 5 minutes, the plane would have had a displacement of roughly 36 miles, because I'm taking the 7.2 times 5. In the next 5 minutes, the plane would have a displacement of 47 miles. And then if you add those two together, you get a displacement of 83. So by using one velocity in the 10-minute period, we get an estimate that the plane's displacement was 72. When we use two velocities in the 10-minute period, our estimate is 83. Nothing bothering anybody. I'm hoping it's simple enough that you're good. Okay, let's do it again. So now here, I'm going to sample every 2.5 minutes. So what I say is, at time 0, the velocity is still 7. I multiply that by 2.5 now. Like I only use that velocity for the first 2.5 minutes. For the next 2.5 minutes, I'm going to use a velocity of 8.5. That gives a displacement for those 2.5 minutes of 21, and then etc. So if you add those four together right here, you get the plane's displacement is now 87. So the more often we check the velocity, the more often we sample the velocity, the better estimate we're going to get as to how much the plane's position actually changed in the entire 10 minutes. Any questions about anything coming to mind from anyone? Please.
Are we going to have to try our best to recreate a function based on?
No. Good question. Yeah, you're not asked to model anything in this class.
How did you choose to use like those numbers? Like how did you choose to use the 7.2, the 8.5, the 9.4? Because those aren't like exactly what they gave us for the...
Fair enough. What I was trying to show is that basically I was trying to make an automated way, Jake, of reading the graph. So I could have just read the graph and wrote down numbers, but I wanted to make it faster. So I created a formula that basically tracks the graph. And so then I'm just checking the velocity more often. And so my choice to check the velocity at every 2.5 minutes is random. I just said, hey, we're going to check every 10 minutes, let's half it again. Every 5 minutes, let's half it again to every 2.5.
And then to find like the values for the velocity, like the 7.2 and the 8.5, those aren't exactly what's on the graph. Is that you just had your formula that you used, or like how did you find those?
No, that's perfect. They're pretty close to what you see on the graph, just not exact. And I just, because I could do the spreadsheet a lot faster if I had a formula, just let the formula do it for me.
Okay.
Does that make sense?
Yeah.
Good question, 2 points. Okay, everyone answer this. Like Jake just said, for this estimate here, 87, that's the plane's displacement. I calculated that by saying in the first 2.5 minutes, the plane displaced itself by 18. Then the position changed by 21, then 23, then 24. That's the plane's displacement for different time periods. I'm hoping this is easy. Raise your hand if you can tell me. Why did I not take into account what's happening at minute 10? Hands up. Like I'm telling you right here, this is the plane's displacement for a 10-minute period. Why am I ignoring what's happening at minute 10? Talk to each other. I want more hands. Come on, talk.
Because we're only looking for the spin in between. The span, yeah, at 10 minutes.
But then you come
Okay, hands up again. Hey, come on, show me hands. Who knows why we are not doing anything with minute 10? Even though a lot of people will tell me, wait a minute, you said that this is the displacement for 10 minutes. Why are you ignoring what's happening at minute 10? Like I'm ignoring it on purpose for a very good reason. Let's go, David.
Because you want to know what's happening from 0 until that point, but not that exact.
Perfect. Yeah, this 10 minutes I'm talking about is a 10-minute duration. So I want to start at time 0. I want to stop at time 10. Like I want to cut it off there. So what I'm saying is for the first 2.5 minutes, I'm assuming the velocity is 7.2. For the next 2.5 minutes, I'm assuming the velocity is 8.5. For the next 2.5, 9.4. For the final 2.5, 9.7. I've now covered the 10 minutes. I don't want to use another velocity. That's beyond what I'm trying to accomplish.
So what we're doing, we're finding all the instances of time in between 0 and 10.
We are paying attention to this time period right here, 0 to 2.5. And we're saying that for that time period, we're assuming the velocity was always 7. So we take 7 times 2.5, that's the 18. 2 for Emmon, 2 for Davis, 1 for everyone else who have their hand raised. Question? Cool. Then following Jake's question, I wanted to keep representing the idea. This is the idea that Derek was referring to. I went every 1 minute. So right here you see, hey, if the plane has a velocity of 7, and we only assume it has that velocity for 1 minute, then, just like what was said earlier, that means in that 1 minute, the plane will change its position by 7.2 miles. And then et cetera, if you add them all up, that's the displacement. Simple question, just trying to give away points. We have several different estimates here. Which one is most accurate? Hands up, come on. And why, of course. Which estimate is most accurate, Naomi, and why?
The one that goes by 1 minute each time.
Yeah, it's all about how often we check the velocity. If we check the velocity frequently, we're going to get a much better estimate. Hands up if you knew. 0.2 for Naomi. Okay, just making sure. Questions? Curiosities? Anything coming to mind? Awesome. And then just because I have a spreadsheet and it's really easy to do, I went one more step. I went and checked the velocity every 1/10 of a minute. Just for kicks and giggles. Raises everything. Oh, sorry, I checked every 1/2 second first. That was fun. Well, I have to just copy and paste once you get the spreadsheet set up. So here's checking every 1/2 of a minute. So notice here I said the first minute was 7.2 miles. Now I'm only going 3.6 in the first 1/2 minute. I get a better estimate. But notice how the estimates are, they're clumping. Like we started out with an estimate of 72 when we checked every 10 minutes. As we check more frequently, our estimates are not as far apart. 83, 87. These two aren't too far apart at all. Checking every 1 minute versus checking every 30 seconds. We get these two estimates. Please.
Will there ever be a way to figure out, like, will there be a pattern of when you change from 1 to, when you're changing to 0.5 change, if there'll be a pattern of what the sum is, what the sum is changing to?
Oh, good question, 2 points. I would say that's possible, but it's not something we will ever investigate. I've never personally investigated that, but it makes total sense that there could be.
Yeah.
Just, we don't check that, so, good question. Here's the last one I did. This is checking every 10th of a minute. And we get an estimate of 90.2. This spreadsheet rolls to the right quite a bit now. So I'm checking every 10th of a minute. Again, it's easy when you have a spreadsheet, just copy and paste. So there you go. Question? Please.
So then this is all leading up to like being as accurate as we possibly could be, right? But wouldn't that require us to check it at every single instant?
So now we're back to 2 for Jacob. We're back to using that word that we have been using in this class a lot. Ideally, we would like to check the velocity at every possible moment in time. So we would like our duration to be infinitesimal. That's calculus. That's calculus. It's like, can we find a way to like make the duration infinitesimal? And Isaac Newton figured out a way to literally make the duration infinitesimal. He also figured out a way to accomplish that without doing an infinite number of computations. Because as Jacob noticed here, I'm checking the velocity every 10th of a second. So raise your hand, you can do the math. If I want to know what's happening in a 10th of a minute, listen close, hands up. I'm trying to find out how much the plane's position changed in a 10-minute period. And here I'm checking it every 10th of a minute. So how many little computations am I having to do on this spreadsheet right here to get that number 90? Hands up, come on, just do the math in your head quick. You can do it. Like I'm doing it for a 10-minute window, 0 to 10. I'm checking every 10th of a minute. So every 10th of a minute, I have to calculate the velocity multiplied by, you can see it, look, 7.2, 10th of a minute. I'm saying the plane's position changed by 0.72. That's how much the plane position changed in that 10th of a minute. So how many of these computations are there to the right? You know, this one, plus this one, plus this one, plus this one, plus this one. How many are there? Come on, do the math. Don't overthink it. It's not bad. There we go. Let's go, Bridger.
100.
So we got, in 1 minute, we'll have 10. 10 minutes, we have 100. Because we went from 0 to 10 minutes. We're sampling 10 times every minute, so we're doing a total number of 100 computations. How many knew? 0.2 for Bridger. Question? Something's bothering Jacob. See if this helps, Jacob. So here I go from 0 to here. This, do you see it now?
Yes, I think. I got confused on a 10th of a minute, but a minute only goes up to 60.
Right.
So I thought it was 6.
Yeah, it's the trouble with time is time is not a decimal system,
No.
right? Yeah, it's like a minute, 60 seconds. Yeah, the 10th doesn't mean a 10th of a second, it's actually a 10th of a minute. You with me?
Yeah, I got
Okay.
it now.
Yeah, this would be 6 seconds, this would be 12 seconds, etc. Okay. Anybody else? Awesome. Okay, so give me a, okay, this means I really am not really following. This means I feel very comfortable. Here's the question, hands down, here's the question. Are you comfortable that if I take a rate right here, 7 miles per minute, and there's a series of questions here I'm going to pick. Are you comfortable that if I take a rate, 7 miles per minute, and I multiply that rate by a duration of time, in this case, I'm going to calculate how much my position changed for those 10 minutes. So show me 1 to 5, how comfortable are you with that idea? Everyone's doing either a 4 or a 5, or a 3.5. Not too bad. Okay, good. Okay, you've got to memorize that today. You've got to memorize that whenever you take a rate, any rate, and you multiply by some time duration, here's what I want you, look, do it this way. For this class, let's go back here, hold on. Here we go. We use Danica's chart all the time. The first column in Danica's chart, we're going to refer to that as an amount. Okay? It's not a rate, it's just an amount. In this problem, that amount is measured in miles. Because we're talking about the plane's position. I would put this in your notes for sure. We're talking about the plane's position. It is an amount. It's measured in miles. The next column in Danica's chart is the rate. In this problem, the rate is the velocity. It's how fast the position is changing. And that's measured in miles per minute. Give you a second to make sure that's written down. Okay, this is like the first day we've talked about this, so you don't really have a conception of how huge this idea is. Up until today, all that we've been doing is trying to understand how to get from this column to this column. That's been your work since August. Seriously, everything you've done has been trying to understand how do we get from this column to that column. How do we understand a position and then find out how fast the position is changing? That's a derivative. A derivative is how fast the position is changing. That's doing this. Okay? Now we're doing this. We're starting with velocity. We're starting with velocity. And when we multiply, listen close, hey, when we multiply velocity by a duration of time, we're going this direction. We're not, now careful, we're not finding position. So it's not a perfect circle. We're finding how much the position changes. So if we know, like we know position, we can take a derivative, find out how fast that position is changing. If we know how fast the position is changing, we can multiply and figure out how much the position changed. That's what the spreadsheet is doing. It's just taking different rates, different velocities, and it's multiplying those velocities by short durations of time to calculate changes in position. This is called integration. Okay? Integration is an extremely simple concept. All you're doing is multiplying, but you're doing it over and over again, and then you're adding them up. That's it. So when I teach you integration, I'm not teaching you anything new. Like you learned how to multiply long ago, learned how to add long ago. Now you know how to integrate. That's all it is. And it gets used in all kinds of applications.
This is a little bit of a stretch, but what you just said about integration, you said integration is like several multiplications and then you add them all up, which sounds a lot like an average where you do a lot of additions and then divide the inverse of multiplication. Are those two things like related in any way?
Interesting. Let me say it back to you. You're right. When we do an average of, we would take all the values, add them together, and then divide, which is kind of like the same as multiplying by 1 over how many we have. There's a strong connection. And I'll show you that connection not today, but near future. Yeah, I can't show it yet, but you're right. Don't forget that. It's very, in fact, what we'll take advantage of is this. Look at me. We'll take advantage of the fact that integration involves, taking the velocity, multiplying by a duration of time to get how much the position changed in that short time duration. And then we do it again, and we do it again, then we do it again. Okay? Because it's repeated, we can actually show mathematically how we can do it in a different order. You can actually do all the addition first and then do the multiplication. And that sounds just like an average. And there's strong relationships. Anybody else? Cool. All right, back to the worksheet here. Okay. So right here, this is integration. All you're doing is multiplying a rate by an amount of time, multiplying a rate by an amount of time, and then adding them up. That's integration. Okay? All they're going to change on you is they're just going to give different stories and talk about different rates. Like I've seen stories that talk about the rate at which the temperature is changing. So instead of being miles per minute, it's degrees per second. But it's not different mathematically, it's just a different story. Question. There was an AP problem years ago that talked about snow falling on a driveway. And it said the snow was accumulating at a rate of 7 cubic feet per hour. Okay, 7 cubic feet per hour. It's just a rate. You multiply that rate by how much time goes by, you can calculate how much snow actually accumulated. Because if every hour 7 cubic feet accumulates, raise your hand and tell me how much snow would have accumulated in 5 hours. Hands up. Snow is falling at a rate of 7 cubic feet per hour. How much will accumulate in 5 hours? Hands, come on, more than that. 2/3, there we go. Parker.
35.
How many do? 0.2 for Parker. Okay. So show me 1 to 5 again. Who is comfortable that if you take a rate, any rate, and you multiply that rate by some duration of time, you will calculate an amount? Show me, who's comfortable? You take any rate, you multiply by duration of time, you calculate an amount. Okay, 2 points for the room. Questions? And then all we do is sample more often and just do it again and again and again. That's integration. Cool. All right. So I got to check my worksheet. My sheet has changed a little bit.
Yeah, because we have to use calculus and higher calculus.
Yeah, I've changed my sheet and I didn't make it much harder to keep up. So hold on.
Benji Bagley could understand what Mitchell was doing.
Come on. Okay. Look up. Hey, my flip chart's a little out of sync with my worksheet, so my apologies. I need to fix that. You're on page 3. Go to page 3, item 3. In your item 3, part A should say what you see. So this should be 3. This is just reminding us information from before. This should say A on your page 3. Is that correct?
No.
That does not matter?
C says A.
It says A on your sheet?
But where C would be.
Oh, where C is, thank you. So not this one here, my bad. So this is A on your sheet, right?
Yeah.
Good, make sure we're together. So it says use a left Riemann sum of 4 subintervals of equal length and values from the table to approximate. This is an integral, right here. Okay? We just talked about integration, that's an integral. Here's how you spell it. So just how it sounds. Integral, yeah. Or integration is the process. Questions? So integral is the thing, integration is the process. Clever. Awesome, here we go. Left Riemann sum with 4 subintervals of equal length and values from the table to approximate that integral. Show computation. This item here is a direct copy from an AP test question. That's exactly the wording they'll use. So here's what you're going to write on your paper. So down in the box at the very bottom where there's lots of space, write the following. Write that integral. You have to write the integral. On many AP questions, if you don't write the integral, you lose a point. So I don't want to ever see you doing an integral without writing the integral. Write that down. Yep, simple.
Now, should we watch
Raise your hand if you can tell me why I put approximate instead of equal. Hands up. Why did I put approximate instead of equal? There we go. Let's go Cougar.
Because you can't measure the absolute, like it's going to be an approximate, it's going to be close. You can't get the absolute value of it.
Yeah, we're going to check the velocity. We're talking about the time period from 0 to 40 minutes. So we're up here, 0 to 40 minutes. We're only going to check the velocity 4 times. So we're going to sample 4 times. If we only have 4 samples, we're not really having a very good estimate. We would need an infinite number of samples to have a perfect estimate. Okay? Yeah, funny. Well said. 2 for Jacob, 2 for Cougar, 1 for the rest. Yeah, perfect estimate. That's an oxymoron if there ever was one. Questions? Okay. My perfect estimate comments thrown me off. I've lost track of where I'm at. Okay. Questions from any floor? Oh, here we go. Now I remember. Sorry. Okay, for the AP test, here's what they'll do. Whenever they want you to approximate, they'll say approximate. Or they'll say estimate. If they don't say that, you're free to put an equal sign, even though there will be examples where what you're computing actually is still an approximation. So I only use the approximate sign when they say approximate. Otherwise, I follow their example, which is if they don't say approximate, I put equal. And when we use our calculator, we're still approximating, but they don't really consider it such a good approximation. They just put equal.
Sorry, could you just remind me what the Riemann Sum term means?
Okay, so 2 for Jake. Right here, where I took the velocity at time 0 and multiplied by 1/10 of a minute, and then I did it repeatedly, that's a Riemann sum.
Okay.
So
And
Riemann, go ahead.
Are all of the expressions that you did Riemann sums then?
Yep.
Even the half-second one and the 1 second?
Uh-huh. Yeah, hey, 2 for Jake. Every single one of these computations right here, this one, etc., they're all Riemann sums. All you're doing is taking a rate, multiplying by a duration of time, you're doing it over and over again, and then adding them up.
Was the one where you took the initial velocity and multiplied it by 10, even though you only did it once, is that a Riemann sum?
Yep. 2 points. Here's the key, Jay. This is an integral. Okay, look. This is an integral. Look what's happening. You all did this when I said, are you comfortable that you can take a rate and multiply by a duration of time and find an amount? Notice the symbols. You're taking a rate, hey, look, and you're multiplying by a duration of time, dt. That's what dt stands for, duration of time. Okay, that means this is computing right here an amount. Okay, look at this symbol. Raise your hand if you can tell me what letter of the alphabet, just gotta use your imagination a little bit, not too much. What letter of the alphabet does that symbol most resemble? Hands up. Come on. Just look at it. Hands up. Come on. Hands up. What letter of the alphabet does that most resemble, kids?
S?
How many votes, Hugh, funny. How many vote that resembles an S? Point two for Caitlin. Hey, look. Because it represents sum. Add them up. So here we are multiplying an amount. Sorry, Gabby, 1 second. An amount by a rate. Sorry, a rate by a duration. That's giving us an amount. And then we are simply adding up the amounts. And that's what the spreadsheet does as well. It's taking a rate, right here, multiplying by a duration of time. This is an amount for that duration. We add up all those amounts, we get the total change. Gabby?
I was gonna ask, what was the difference between a Riemann sum and like integration?
Oh, I'm paying a ticket for that one. Okay, look here. Look. Make sure your phones are put away. I gotta get out my little booklet to write down who never gets to retake, but there's really only one difference between an integration and a Riemann sum. And we've talked about it, I just may not have stated it. Richard, if you can tell me, what's the only difference between a Riemann sum and truly integration? There we go. It's really, once you say it, you go, oh, that's easy, I just didn't think of it. Like, what's the only difference?
Is it like integration, like infinitesimal?
That's it. Riemann sum, Gabby, means that our time durations are fixed. Like, this is a time duration of a half of a minute. This is a time duration of a tenth of a minute here. This one. If it's truly an integral, it's a time duration that is an infinitesimal amount of time. Otherwise, they're exactly the same. Does that answer your question?
Yeah, because I was gonna say, before you had said like, that they're both taking rates and adding them up, but that makes sense that it's just infinitesimal and not.
Yeah, there's no other difference, okay? And that's why, Gabby, they say here on the worksheet, so point if you knew that, 2 for Zane. They say use a left Riemann sum to approximate the integral. So you're doing the exact same thing, you're just doing it with a dt that is not infinitesimal. 2 for, I need Debbie too, so anybody else? Okay, my hope is that I hope you know by now that I am a huge believer that the idea of the class is not to learn to do stuff. The idea is to understand the idea and then do stuff with the idea, because it's much more powerful. If I can get you to be really comfortable with what integration is, then it's not hard to help you learn how to use integration for lots of purposes. This is what integration is. It's just multiplying again and again and again, and then adding. Okay? And the symbol tells you that. It tells you what to multiply, and it tells you that you now need to add them up. And it tells you how often to do it, like for what time period, 0 to 40. Okay? Questions? And somebody mentioned the word antiderivative earlier. This is not an antiderivative. There is a relationship there. We won't talk about it yet. This is not an antiderivative. This is an integral. Please.
So out of curiosity, will the 0 ever be on top of the 40? Would there ever be an instance, or is that just breaking the laws?
Look, 2 for Cougar. Everybody can answer this. If I put the 0 here on the top, where the 40 is, and I put the 40 on the bottom, I'll now be integrating what I would call backwards in time. So your duration in time will now be some negative number, because you're going backwards, but mathematically it works just the same.
Okay.
I avoid doing that because it tends to lead to errors. So I'll teach you to just always go forward, but you can.
Is that like a universal equation, like the integral with the 40 and the 0 are obviously will change, but like the integral and then the velocity d of t?
Here's the universal, 2 for Jake. You're going to integrate from some, this goes back to Spencer's comment, 2 for Spencer again. Hands up. Simple question. Is the 0 a moment in time, a duration in time? What's the 0? Hands up which? Is the 0 a moment in time or is the 0 a duration in time? Let's go, Mark. How many knew? Point, 2 for Mark. So what's universal, Jake, is we'll start at some moment in time. It doesn't have to be 0. We'll go to some other moment in time, whatever, and then we'll take a rate. It doesn't have to be velocity. It could be the rate at which temperature is changing. So it could be T prime of little t like that. And then we'll multiply that by some duration of time. That's the universal. In reality, it doesn't even have to be time. But for our class, that would be most common.
What is T prime?
So I just made it up and said this is going to represent the rate at which the temperature of a molten piece of steel is changing.
Is there an even more universal symbol that we can use in place of T and T prime?
Oh, good question. I don't think so. Like, I think it'd be fine to just do this. I think I did this in some notes I'll give you eventually. I just said rate dt. Because I can use any rate. So, 2 points. Please, Haley.
So it says you use the Riemann and
Riemann, you're fine.
Riemann sum with the 4 subintervals of equal length and value. But since our table, the time increments are the same, it's always 5. Can we just pick any 4 periods of time, instances of time to use for the problem?
2 for Haley. But look, this goes back to Gabby's question. 2 more for her. There is one other difference. You needn't concern yourself for this class, but it is a difference. It's Haley's question. Which values do we pick? The Riemann method is a specific method which will tell you which values to pick, and I'll show you that. There are other methods we don't learn for this class that would pick other values, but for Riemann, we just followed his method. So that's very good. So here, right on your paper, you've got this written down already. This other stuff was kind of questions. You've got the approximate sign. Now all you do is do what it says. Velocity times duration of time. It says left Riemann sum. That means we go to the table. We got 4 subintervals of equal length. So here's the first subinterval. Here's the second, third, here's the fourth. Okay, 4 subintervals of equal length. Warning, this is really subtle, but I have seen people do the following and then get super messed up on a test. Instead of drawing these little brackets like I'm doing to show the first subinterval, second subinterval, third, and fourth, they go like this. They go, oh, first subinterval. Come on, Pen. And then they go second subinterval. And then they come to my desk and say, I only got 3. Like, here's my first subinterval, here's my second, here's my third. It says 4. How am I supposed to get 4? Like, it's messed up. Like, they're leaving out time. They're going 0 to 10, then they're going 15 to 25. Well, what happened to 10 to 15? So don't draw vertical lines, draw little brackets. It solves the problem. 0 to 10, 10 to 20, 20 to 30, 30 to 40. Please, Haley.
What if it said to do like 5 subintervals of equal length?
2 points, 2 points, 2 points. For our class, they won't do that to you. If they give you a table, they'll make a way that it fits. Yep. Okay, we've got to hurry because the bell's going to ring. All that's left to do is it says left Riemann sum. Remember, no homework tonight. We'll just pick this up again on Wednesday. That means you go to the first subinterval, you pick the left side of the subinterval. And you pick that velocity. This is Haley's question. You take that velocity and you multiply by a duration of time, 10 minutes. Then you repeat the process for each subinterval. So now I go to the next subinterval, I pick the time on the left, I pick that velocity. That velocity endures for 10 minutes. I do it again for the next subinterval, 4.5. multiply that by 10 minutes. Last subinterval. You are required to write on your test exactly what I'm writing, so you can't do it in your head, you'll lose points. It is a requirement. Questions? And you just write down what it is. So you do the math and write it down. And I'll cheat, turned out to be 234. So. No, that's wrong. No, that's right, 234. Good job, you guys.
2, 3, 4.